Now that we know that the momentum of the center of mass is just equal to the sum of the momentum of each particle in the system, this tells us that if we have one particle, so say particle 1, and it undergoes some interaction, so that now its new momentum is equal to its initial momentum plus some impulse. Well, now, as we can expect, our center of mass is going to have a new momentum, which is equal to the momentum of the first particle, the initial momentum of the first particle, plus the impulse. And if none of the other particles had their momentum changed, then those just remain the same. Which means the new center of mass momentum is the initial momentum plus the amount that we changed the first particle. So we see that by interacting with just a single particle, it changes the total momentum by the exact same amount. Well, we can take this even further. What if instead of just one particle being affected by this interaction, what if it affected multiple particles? In other words, we deliver some impulse to the center of mass, and that's the sum of impulses acting on particle 1, on particle 2, and any other particles that impulse might have acted on. Well, once again, the new center of mass momentum is just equal to the initial center of mass momentum plus the center of mass impulse, which is the sum of all the other impulses. So this becomes really convenient. We can, even if we interact with a single particle, since we're delivering that momentum to the system, we can say that the total center of mass has its momentum shifted by the exact same amount, no matter how many particles are involved in the interaction. Next time we're going to look at something even more interesting. We're going to look at what happens if instead of this external interaction where we're adding or subtracting a momentum from the system, what happens if we look at the interactions between the particles all of the particles that are contained in the system. And so we'll see what happens next time.